This is going to be a brief Math-cad tutorial. There's no way I could give you a Math-cad tutorial that shows all the different features. But these are the features that I use a lot in classes and in work and so forth, and people ask me the most questions about. Okay, let's get started. First of all, you're going to have a love-hate relationship with Math-cad. Nothing can do what it does, but nothing will frustrate you so much. The other thing I've learned is make frequent backups. Not just saving, but save as a different backup file name every once in a while. I've had problems where Math-cad files will just become corrupt. If you ever find yourself trying to save a Math-cad file and it just hangs, what I usually do there is copy the whole page and open a new document and save it. It works. It works every once in a while. So just some warnings up front. Okay, first thing to know is that there are 5 different types of Math-cad equals signs. This is something that confuses a lot of beginners. The first type is the definition equals. So in other words, if you want to say this particular variable, x1 in this case, is equal to 5, you hit the keystroke colon, and you can use that equals. If you want to evaluate something that at the end of an equation or something like that, you know, x1 times y, that is just the keystroke equals. Now notice the way Math-cad works is it first goes through, it does everything sequentially in order, okay, just like a regular program. You notice here, I had defined x1, but I hadn't defined y yet, and there was still a number, 20. That's because I defined y using something called a global equals. What global equals do is it tells Math-cad, hey, I want you to define y as 4 for the whole sheet. So you can actually define global equals down in a local convenient place in your program where you'd like to put a lot of inputs, and it'll be defined anywhere. So that's the triple equals keystroke tilde. If you define, you can define global functions as well. But just know that if you define a global function that requires a global variable, those have to be in order, okay? Because it needs to know, if everything's defined as global, it needs to know what goes first. Okay, there's Boolean equals. This is a logical test. Is A equal to B? If it's true or false, you have 2 different options. Okay, those are used in programs and so forth. And then there's also local assignment. This is if you want to define z as equal to xx over ww within a program. It's only done as a program. It's defined this way. I'm not sure why they use that form, but that's the way it's done in a program. Okay, here's some example functions and units, or using units. I could have written a simple function here, but I wanted to show you that you can actually define a function. It can be piecewise. You know, a function can even be a program. This is actually a program. And to define a program, you can use the programming toolbar, and you notice here you just hit add a line, and it begins your program. So this program is constant. It's 42 inches. You notice, and you just type 42 in. If y is less than equal to 8.5 inches and 9.7 inches otherwise. I'm also defining this. It's a quarter chord function in a similar way. And you notice the examples I'm going to be showing you, a lot of them are from aerodynamics or stability and control. And I've also defined a wingspan. And here's an equation. This is one of the things I love about Math-cad. I want to define wing area. Wing area is an integral. I can write it in Math-cad the exact same way I would write it by hand. And in this case, you see my wing area is 0.92 meters squared. Well, let's say I want to know that in feet squared. So you click on this and you see this little black box here. I can type that into that black box and type feet and then the hat squared. Boom, and it converts it for me automatically. Okay, I can do the same thing for C-bar. Or let's say I want to know the aerodynamic center in inches. I could do inches. Oops, you see I made a mistake there. That should have been feet. Okay. And here's a plot of these different functions. Plotting in Math-cad it can be tricky, but once you learn it, it's really useful. And in fact, something I'm not going to show you here, but if you're interested in, you can even animate plots. There's an animate function within Math-cad. But over here for every one of the things I want to plot, I've got plotted here. The black is actually the wing. You can see it's kind of a discretely changing wing. The green dashes are the chord lines. The integrated aerodynamic center is equal to the red dots. And you see I plot each one of those functions versus just some random variable, in this case y1. Okay, let's talk about symbolic operations. This is one of the most powerful features within Math-cad. Once again, I'm not going to show you an exhaustive tutorial, but just some highlights that you might enjoy here. Notice if I've got a complicated equation that's got a lot of terms in it, and you notice here, I mean, I could do this equation by hand, but sometimes you know your equations get so big it's easy to make mistakes. Like I could have combined the squared terms here, and I could have divided through. Well, I can do it symbolically. In this case, I just use simplify. There's a lot of different features you could have used: factor, expand, coefficients, collect, so forth. But I just use simplify in this case, and boom, it simplified it down to the polynomial. Here's an expression where I actually wrote it using imaginary numbers too. This would look like the poles from an eigenvalue calculation. I here is not the letter I, it's actually the definition imaginary unit within this calculator function here. And I tell this to simplify, and there it is. This is the polynomial expression that results in those eigenvalues. Remember, you can use, you could use a quadratic equation to solve this equation, or you can just solve it symbolically. You can also do that with a given find. I'll show you that later. And then what if these coefficients were actually unknown? Well, it'll do that too. You see the symbolic expressions for those. I use this feature quite a bit. So I define a function. Lift coefficient in this case is a function of angle of attack. It's CL0 plus CL alpha. So these two are constants, but I haven't defined them yet. I can differentiate. It has a differentiation operator you see within this calculus toolbar. I can do derivatives or multiple derivatives, definite integrals, indefinite integrals, sums, products, limits, all sorts of things here. But in this case, if I just wanted to differentiate a function, in this case a simple linear function, boom, there it is. I could have also done it if the constants were defined. So here are all the constants defined. There's my function. And then take the derivative, and it actually gives me the answer for that. And then just like you can do symbolic differentiation, you can do symbolic integration. Here's the integration of phi squared with the limit 0 to a. This symbolic engine is really useful when you're doing uncertainty calculations. If you've ever done these, you notice that if you have a complicated equation where you need to calculate the propagation of uncertainty, you got to take a whole lot of derivatives and then combine them all together and put them under a square root sign and so forth. Well, I could do that here. Notice the equation I define would just say it's the dynamic pressure. Okay, and the uncertainty equation is the derivative with respect to rho times, or of the equation times the uncertainty in rho, and same thing, the uncertainty in V. And you see there's the symbolic result, so now I could actually use that. So you can see how useful this would be in really complicated equations with a lot of variables. Given and find blocks are really fundamental to Math-cad. It's one of the most powerful features. You can use them for a lot of different things. I'm going to show you 3 different examples here. First one is a symbolic example. That I had told you before you could do symbolic given and find. Here's a system of 2 simple equations, and I don't know K1 and K2, and I want to solve for those. If I use the symbolic equals, it'll actually solve it. Minus 7/4, K1's minus 7/4, and K2 is 0. If I tried a regular equal sign here, I'd get an error. So let me do that exact problem. This exact same problem again. I'm going to right-click on each one of these and select Disable Evaluation. I'll tell you what those are in a minute. So same exact equation. The only difference is I hit the equals instead of the symbolic equals. Then you see I get a variable as undefined. Because what this is trying to do now is use a numerical solution technique to find the solution. And so the symbolic equals here, it's not going to work because it needs something. Any one of these symbolic techniques requires initial guesses. So I can just put in initial guesses here, and boom, it finds the answer. Okay, these initial guesses can be anything. You get the same result. Okay. Sometimes for you notice here, if I right-click on the find, there are different solution techniques that you can use. This was a linear equation, so it auto-selected linear, but there are all sorts of Levenberg, Marquardt, conjugate gradient, quasi-Newton, all sorts of solution techniques that you can use in a given and find. This case with multiple solution possibilities, this shows you how initial guesses are so important. In this case, I want to find the solution to f of s, or f sub s of theta is equal to 0, and the equation is just sine theta. Okay, you notice sine theta's got a whole lot of places where it crosses 0. So which one of these solutions is it going to pick? Okay, so here's the given and find block first. Given f of s equals 0, or I should say fs of theta is equal to 0, and this is the function we're evaluating. Find where that's 0. And I have initial guess up here, notice in yellow. I like to put things that I input, I often highlight yellow. And the way I do that is I right-click it, go to Properties, and then you can highlight the region, and then you can choose the color here. Okay. Let's say if I selected 1, the green is my guess, and the blue is my solution. Okay. What if I selected 2? Oh, now it jumped over to this one. It found this solution. So usually, you know, the closer your initial guess is, the better you're gonna be to what the local solution is. You know, 3 You see it still found that same one. This is an interesting one. If I hit 5, it didn't find this one or this one. It jumped out and found this one. So that's why initial guesses are really important in any of your numerical solution techniques. So keep that in mind. You can do matrices, matrix calculations, cross products, dot products, matrix multiplication, all sorts of different things in Math-cad. You can also do eigenvalues, which is really useful to us in dynamics. So this is a 4x4 matrix. In fact, it's the A matrix, or the stability derivative matrix for the longitudinal dynamics of a Ryan-Navion. And if you want to find the eigenvalues for this, you literally use the built-in Math-cad function eigenvals. And there they are. And you can see here there's the short period and their long period roots. And here I'm just plotting them. And on this axis, I just, IM means select the imaginary part of this variable, and RE means select the real part. And so you can see the phugoid here and the short period roots. So very, very, very simple to do matrices and matrix manipulations in Math-cad. Can do a lot of programming in Math-cad, but it takes a little getting used to. As I showed you before, using the add line feature within Math-cad, that's how you develop these programs. This program I wrote here is just a counter, and what you input in this case to this function, this program function is NC. How high do you want to count? You notice it says, okay, k is equal to 1, while k is less than NC. I count k. This is actually an array index now. Okay, so you notice if I have a function over here, let's say if I say t, if I hit the period, let's say 1. Okay, that's actually just a variable t1. All right. If, however, if I hit the, I guess that'd be the left bracket and say 1, this is actually array index 1 for t. It's kind of unfortunate that sometimes it's hard to tell the difference. T1 versus T1. You see there's a subtle difference, you can barely see it. Okay. So what this does is then it just increments the counter, and then when it gets to NC, it outputs it. And so here you see if I hit counter 5, there you go. There's an array. And you notice it started at 0 because I have the Math-cad options. Math-cad option, the array origin set to 0. If I set that equal to 1, it would start at 1. Okay, I could put in counter 3, and I'd get that. And you notice I can select individual numbers. If I select the second element, you know it's 2. Here's how I could use Math-cad to solve a nonlinear differential equation. We have these a lot in engineering, and especially dynamics. So let's say I had F equals ma for a spring mass damper system. So there's your ma. And let's say you could have in general the damping is some function of how fast it's moving, and the spring is a function of where it is. These could be totally nonlinear. So let me define the damping as nonlinear. So you notice it's actually it's a function of the direction you're moving, sine SIGN of v, and also the speed squared. So you could see it's some kind of viscous damper. And the spring is just a linear spring. So once again, the great thing about Math-cad, I can kind of write this in state space form just the way I would. So put all the single derivatives on the left-hand side. So ddt of x of t is v of t, and ddt of v of t is equal to minus 32.2 over 5. And there's your damping function, your spring function. This kind of solver requires the initial conditions on the inside. You notice I have to use the Boolean equals here within a given and find block. And then I use something called ODE solve. Okay, and this ODE solve is going to return the two variables in time, x and v, from 0 to 0.25 seconds. That's actually 0.25 seconds. And it uses atoms or backward differencing depending on the stiffness. And you can write select on it and select different types of solution methodologies if you want. And then here are the plots of the solutions for those equations. You see it's a little bit different than what you'd expect because of that nonlinear spring. But relatively simple to do very complicated nonlinear differential equations within Math-cad. Tables are another thing in Math-cad that can be tricky. I'm not sure why the cut and paste is so difficult, but it is. And this is, we often use these if you've got airfoil data from a program. Maybe it's in Excel and you want to copy it into a table over in Math-cad. So the first thing you do is you right-click someplace and insert table. Okay, and then you'll get something like this. And then you name it. So my data has 4 columns. So I go ahead and, you can pull when you've got a table over here. You see you can pull on these tabs and you see you can open them up. So I've opened this one up to 4 columns. And then what you need to do is, you see what I mean by Math-cad can be frustrating. So what you need to do is left click in the farthest right column and then drag left to highlight the column. So I do this and then paste. Okay, and there's the table. Okay, then if you want to access that data, you use these brackets as sort of an exponent. So this selects the first column, second, third, fourth, and I could even plot these. And these are actually functions. So you notice what I have plotted here is the actual data or the circles from the table. But then I've also created a function that linearly interpolates within the data. So it's nice, you can input data from a table for an airfoil or a wing or whatever, and actually create a lift and drag and moment function out of it. So that's what these are here. Range variables are one of the most common things in Math-cad. To define them, you just hit the semicolon. And when you define a range variable, the first variable is where you start. The second variable is the next number. So this actually the step size of a range variable is equal to this number minus this number. And then here then you hit the range variable keystroke, semicolon, here's where you end. So there's the range variable I defined above. You can actually do calculations with it. Now notice that the range variable is not a vector or an array. Okay, those are separate definitions. These are listed kind of like a table, where this is an array. You can use range variable as array indices. And you see I just defined this array using a couple of two range variables. So very useful. And then finally, numerical integration. In this case, I want to calculate the takeoff distance of a plane, including the effects of drag, rolling, friction, constant thrust, and show the units. So I derive the equation, and here it is. This is written here just the way I'd write it by hand. Put in all the different variables of interest, and then Math-cad automatically does it for me. And it looks like, this particular case, it takes about, 1,100 feet to take off. And that's a quick overview of Math-cad. Don't forget to use this little question mark up here, help. It can be very helpful. Use the search command, and you can find all sorts of things. And then these quick sheets you'll find in help are really useful. Quick sheets are actual Math-cad example sheets that you can use. So be patient, play around with it a bit, and enjoy it. I think you'll find Math-cad is a great tool.